That is what we find. So more electrons are moving from lower energies to higher energies. It is important to note that this function doesn't necessarily say that you have an allowed energy at E. Whether there is an allowed energy state at an energy E is decided by your density of states function and allowed energy levels. If there is an allowed state, or there are states within an energy interval dE around that point, then what fraction of these states are occupied is what is given by this function at any temperature T. So to understand the shape of this function, one can actually again consider an analogy. Okay? Again, you have a water in beaker analogy for this. Let's say you have a beaker which is filled with water. And now, supposing we agitate this beaker, and now try to see how the surface of the beaker is, the surface of the water, not the beaker, surface of the water in the beaker is. Okay? So there is an animation to show this. So here the top of the water surface is calm. Okay, so no agitation. Now let us say I agitate the beaker. So you find a disturbance, and what is happening there is some amount of water from below the surface is going above the surface in some place, and some other place there is a void from where the water is transferred. You increase the agitation. There is more likelihood that you will find water above the top surface, corresponding to the calm situation. Okay, and you increase this agitation even more. Okay, let me show you the mean surface here, and this is the agitated picture. Okay, so what we are saying here is, if this is the picture when no agitation is present, when agitation is present, it would be something like this. Something like this. So water from here has gone there. Now increase the agitation, it could be something like this. If I were to now plot, I replace this energy by height. And instead of the Fermi level, I call this as mean top surface of the liquid. Mean top surface of water, this location. And what I am plotting here is the fraction of the beaker volume occupied as a function of height and agitation. So fraction of the beaker volume that is occupied as a function of agitation, let's say height first, because there was E first, so E is analogous to height. So F stands for fraction of beaker volume occupied. Then in fact you will have a picture something like this, where this is increasing agitation. Your plot would look something like this. So this is for zero agitation. The red line is for zero agitation. So when there is zero agitation, your surface, water surface is like this, and let us say this is height h0. This is h0. So above this h0 you have no water, and below h0 the entire beaker volume is occupied with water. So the fraction of beaker volume occupied is 1 below h0, above h0 it is 0. Okay, so this is no agitation. The red line is no agitation. That is the reference. As you increase agitation, you find some water above that surface, and that, therefore, the fraction of water present, okay, is non-zero above the surface. But you go higher and higher in height, definitely the amount of water, probability of finding water is going to be less and less. Okay? If you increase agitation, you are likely to find more water. Okay? Above height h. So this is an analogy where the water in the beaker is analogous to electrons. The beaker volume is analogous to the allowed energies. The height is analogous to the energy. Okay? Agitation is analogous to temperature. And the fraction of beaker volume is analogous to the fraction of occupied states. And finally, what is very important is this mean top surface is analogous to the Fermi level.